All right, 1.4. Continuity and one-sided limits. All right, so continuity is a big issue. It's a very important issue for calculus. It's the base. We have to have a base understanding of continuity before we get into derivatives. And integrals. So what does it mean to be continuous? If on an interval, a function doesn't have to be continuous everywhere to be continuous on an interval. To be continuous means that it's smooth, and every single point exists in a smooth curve between 2 points. So if I'm going from A here to B here, this function, we could say it's continuous if you could trace it from one end to the other without lifting your pencil. Okay, that would be continuous. Now, mathematically, there's actually 3 parts to being continuous. First of all, for any point C in between A and B, first of all, f of C must exist. Any point. It has to exist at some point in there. Part 2, the limit as x approaches C, f, C of f of x must exist. So the limit has to exist as well. And part 3, those two things have to equal each other. The limit as x approaches C of f of x must equal f of C. So those are your 3 rules for continuity. On and open it. It's easier to understand when you start looking at things that aren't continuous and how they break these rules, which is what we'll do next. I'll give you some examples and we'll go through and I'll show you different scenarios that break these rules in different ways. Okay? All right, so let's look at a graph. So look at a sketch here that's not continuous. So let's say it's here. Now, which rule of continuity does this one break? First of all, does f of C exist? Here's C. Yes, it does exist right here. Now, does the limit as x approaches C exist? No, the limit does not exist because the limit approaches different things from either side. Therefore, the limit doesn't exist. And if it doesn't exist, we can't go to number 3. Okay, so this is a typical limit does not exist. Another one, just very simple. Does f of C exist? No, it doesn't exist. Not that we know of. It does not exist. But what about the limit? The limit does exist, but f of C does not exist. So we're done. We don't go to step 3 because neither one of those things happen. Now, could you have the first 2 being true and the third one being wrong?
Yes.
Okay, let's look at a graph of that one. If you have a hole in the graph and a point above or below, so does f of C exist?
Yes.
Does the limit as x approaches C exist?
Yes.
Now, do those 2 numbers equal? No. So this is not continuous. Blush. Now the same thing can happen with vertical asymptotes. If we have some vertical asymptote in here, so this one just fails everywhere. this is C. Does F of C exist? No. Does limit exist? No. B? No. It's just no, no, no. We get no's everywhere with vertical asymptotes. But I've got to show you this one. College Board loves this question. Is the function continuous at C? A and B? Here's A, here's B. Alright, here's local color. So, is the function continuous at C? Exactly. Okay, they'll put a vertical asymptote in a problem, and they'll draw your attention to the vertical asymptote and ask you if the function is continuous at C. Well, this is not C, this is C. C is here. Yes, it's continuous there. Okay, it's not continuous at the vertical asymptote, but it is continuous at that particular C value. Okay, so they do like to try to throw in a trick question every now and then.
Yeah.
Oh no, it is.
It is, okay.
It is continuous at that particular C value.
But not.
Not at D, no. And it's not continuous over the entire domain. But it is continuous at one specific value. Okay, it's continuous there. All right. Okay, now let's talk about one-sided limits. Let's say we have this graph. Say we have a step function, and this is, say, 2. This is 5, 7. First, and this is f of x. So what is f of 2? F of 2. 7. Okay, so it does exist, right? Now, does the limit exist? No. No. But we can break this down a little bit further than just limits. We can actually look at one-sided limits. We can look at what is the limit as x, are y'all watching this? The limit as x approaches 2 from the left. If you see a superscript negative here, that means from the left. So what would the limit as x approaches 2 from the left be? 7. So the limit as x approaches 2 from the right, a little superscript plus will mean from the right. So what is that limit? That's 5. Now, if these two, if the left limit does not equal the right limit, then the overall limit does not exist. But it can have left and right limits, even though the limit doesn't exist at that point. So those are one-sided limits. It's just from the left or from the right. You just have to look at those plus or minus signs. Yes?
Just to understand here, so if there's no negative or positive, then it always
It's
means
an
from both
overall.
sides.
Yes, it means from both sides. It has to have a little plus or a minus in order for it to be a right or a left. Yes, very good. Okay. So, remember Charles Law. Charles Law. It's talking about absolute zero. That's physics. It's on the Kelvin scale. Okay. So, the last thing we're going to talk about in this section is the intermediate value theorem.
Today.
Yeah. Intermediate value theorem. Alright, so it says, here's the thing. If f is continuous, on a closed interval, from A to B, that's bracket A, comma B bracket, and f of A is not equal to f of B, so they can't be the same height at endpoints, and K is any number between f of A and f of B. Then there is at least one number C C on the interval A to B. Oops. Such that f of C is equal to K. Isn't that awesome? So do you understand it?
I got it.
So if you got two numbers here, okay, you've got a continuous function over a certain interval, and there is included in the range, the two endpoints, there's every single number between them included somewhere.
Yes. That's very good.
Like, you got a continuous function.
Let's draw a picture. Yes. I'm very visual as well. So we got A to B. Now f of A cannot equal f of B. Okay, so I'll put f of A here and f of B over here. Now it's a function and it's continuous, right? So it doesn't matter what it looks like in between, but it could be anything. But it is continuous all the way from A to B. Now K is any value between A and B. K resides here, right? What? K is any number between f of A and f of B. Sorry, ooh, bad. That's what I was thinking. C is down there. K resides in here. K is any number between f of B and f of A. Then there must exist, for any one of these values, there must exist a C in here, no matter where you choose it. If you choose a C here, it's going to hit that K right there. So if you pick any K value, if we picked K to be up here, we come over, across, and down, there's C. There must exist a C between A and B so that f of C equals K. C can't be outside. Basically, it eliminates this situation.
Where they're
Yeah, it's not a function. Okay. Or it goes outside. C might go for, if we pick a K value, okay, and C is outside, here's A, here's B, C would be outside. Or if it was a straight line. Yeah, if it was a straight line, then that wouldn't work.
Over above.
A wouldn't be below or above B. Okay? The intermediate value theorem is an existence theorem, and I've never seen a question about it in the exam. It's just we use the intermediate value theorem to talk about other theorems as well. So we have to discuss the intermediate